So in this case, we are going to consider as a continuation working with the graph of the derivative of a function. The derivative of a certain function produces a graph. All right? You are given a certain function f of x, which is x cubed. The derivative of that function, all right? If you have to apply your derivative, remember, I'm going to drop the power here. You subtract 1. So 3 times 1 is going to be 3x squared. 3 minus 1, which is what? Which is 2. What you have on the derivative here is a function as well. F of x, this one was what? A function. So when you differentiate, you're obtaining a function. If you are to find the second derivative of these 3 times 2, that's 6x, a function as well. So the derivative of a function is itself also a function. So therefore, we can have the properties, we can draw, we can sketch that first derivative, or it is the second derivative of a certain function as a what? As any graph that is going to be formulated from there. So it differs with the type of function that you're given before. All right, but before that, let us just have this statement. It is important for us to have this. So what I'm simply saying here is that the derivative, right? If you have to consider the derivative of a what? Of a function. The derivative of a function is itself a function. It is itself also a what? Also a function that we must consider. So what is important on the graph of the derivative are the properties from the function where we obtained that derivative. You must work with the properties. Let's take for an example the derivative so that you can understand me much better. Let's take for an example the derivative of a linear function. The derivative of a linear function. All right? Given a linear function, we know that we can differentiate, remember, from our derivatives with respect to x. Ax gives us a linear term when you're given ax. So let's say we are given a linear function. In our case, f of x is equal to whatever expression that you're given. You can have ax plus b, you can have mx plus c, whatever, representing what? A linear, where the highest exponent is 1. This is your function. What about its derivative? The derivative of this is going to give us what? Ax, remember, gives us what? Gives us a. The derivative of a constant is what? A 0, so there is nothing here. So it is what? Equal to a. And this is a function that you are referring to. Y is equal to a. Y is equal to a constant. So you're going to notice that the derivative of a linear function gives us a what? A straight line parallel to the x-axis, because the line y is equal to a. This here, it simply means, because this is now to be considered as another function for the what? For the derivative. So for that derivative, we are saying the graph that you are going to consider is y is equal to a, the derivative, the graph of the derivative. So considering the line y is equal to a, it is a line parallel to the x-axis. Remember, guys, from our grade 8 mathematics, lines parallel to the x-axis, those are the lines of y is equal to what? The constant, the value of y for that where the line crosses or passes through the what? The y-axis. So meaning to say whenever you are to draw the graph of the derivative of what? Of a linear function, you are going to end up with the what? With a straight line that is parallel to the x-axis. All right. So this one here, let us say, all right, okay, let me just write in short. Let me just write in short the derivative. All right, the derivative of all right, the derivative of a linear function So we saw that it is going to give us what? Y is equal to a, gives us a line that is what? Parallel to the x-axis, all right? So is a linear also, or simply is a what? Straight line parallel to the what? X-axis. Parallel to the x-axis. So this is the condition when you have a linear function originally, if you find its derivative, is going to be y is equal to a, the coefficient of x. So if it is a -5, y is equal to -5. If it is a 2, y is equal to 2, like that. So that is what you obtain on a what? On a linear function. So in this case, we do not have much to consider. Where we are going to consider much is on this one, the derivative of a what? Quadratic function. The derivative of a quadratic. All right, we're going to consider a quadratic function. We want to see what will be the properties for this. So if you are to consider, guys, a quadratic function is the one where we have got our f of x equal to ax squared plus bx plus c. So its derivative, if you're going to note, you're going to drop the power here, multiply to a, so that's 2ax, subtract 1, the derivative of a linear term, that is going to give us b, a constant, that's a 0. Looking into this here, 2ax plus b, it is a linear function. The highest power on x, the exponent on x is what? Is 1. That's a linear. In our case, we are obtaining a linear from the derivative. We are obtaining what? A linear. So meaning to say here, that's the derivative of what? The derivative of a quadratic function is a what? Is a linear function. You obtain a linear function from differentiating a quadratic. So let's say we have got, remember a quadratic, it can be concave up or it can be concave down like this. So let's consider to say, all right, I'm just gonna have this as my y-axis. I'm just gonna have two graphs here. All right, from the same. All right, this is our y-axis like this. So let us say we have got a quadratic function. That's our original function. All right, and it has something like this, a turning point. where it is what? Concave up and it has a turning point like this. You are going to notice that the turning point represents, at the turning point, that's where we have got the first derivative, and that's equal to 0 at the what? Turning point of what? The quadratic, of our quadratic, the original function. Remember the properties at the turning point, the first derivative is equal to what? 0. And that is the one, the first derivative representing what? Our linear function. So if this was drawn, it was going to be something like this with an increasing, a positive gradient, where at the turning point, the value of x at the turning point is the same as the value of x here for the x-intercept of our linear function, this one. It will be the x-intercept. This is the graph of what? F. This is its derivative. It becomes a linear. So it's the same when it is concave down. We are going to be having this with a line that is having what? A negative gradient. So what I want you to notice here is this part to say that at the turning point, where you have the turning point, the first derivative is equal to 0. Remember, the first derivative represents what? Your linear function. So if you are taking a linear function, let's say is 2x plus 3, your linear function, then you equate to 0 like this. What are you finding when you are equating to 0? You are saying the value of y is equal to 0 for that linear function. For that linear function, the value of y is equal to what? Is equal to 0. So you are calculating the value of x, which is what? The x-intercept. When y is equal to 0, you're calculating what? The x-intercept. So that's at the turning point. The value of x that corresponds from the turning point is what? Your x-intercept of what? Of the linear function or of the derivative. That is the condition that you're going to have at the turning point. All right, so here I can just indicate this in this manner to say, for the first derivative, which is this linear function, it has x-intercept, where our function, where our f, original function, here is what? A turning point, where f is a turning point or stationary point. Where we have a turning point, the value of x is the same as here. So this is our x-intercept for the what? First derivative. This is very, very important for you to note. From what? From our quadratic function. These are the properties that you're going to have. The first derivative is the one that you consider has x-intercept where f has a turning point. All right. Then when it is a cubic function now, all right, the third one that I'm just going to consider is the derivative, all right, of a cubic function. The derivative of a what? A cubic function. When you are to consider a cubic function, remember that f of x is equal to ax cubed plus bx squared plus cx plus d. Its derivative is going to give us what? Remember, we differentiated this before. You multiply here, that's 3ax squared. You subtract 1 plus 2 times b, that's 2bx. You subtract 1. Cx is going to give us c for this linear. A constant gives us what? Gives us a 0. Remember that. So this is your first derivative, where the highest power is what? 2. So meaning to say, you obtain what? A quadratic from a cubic. What you're going to obtain at the end is what? A quadratic, where the highest power is 2. So that's the derivative of what? Of a cubic. So the derivative, right? The derivative of a cubic function is a what? Is a quadratic. Is a quadratic what? Is a quadratic function. This is the idea that you are going to use. So I'm just going to give you an example of a cubic function where a is greater than 0, like this, all right? So let's say you were having a cubic function, all right? We have got a cubic function like this. This is our case where we've got our f, and this is our y-axis like that. I'm just going to have this one to correspond to the main points of our f. From f, we have the turning points, which is here, it is a turning point, and also here there is a turning point. And also the point of inflection in between the turning points. Remember, that's where lies our point of what? Inflection. So it follows that the quadratic function that you are going to obtain, all right, in our case, for the value of a, if a is greater than 0 on f, therefore a is also greater than 0 on what? On its derivative. And we said the derivative is a quadratic, so where a is greater than 0, it is going to be what? Concave up. If your cubic function, your a is less than 0, also for quadratic, a is less than 0. So it will be concave down. So in our case, our a, considering that it is greater than 0, that's the shape of a cubic function that we have. So therefore, our quadratic is supposed to be concave up. So it follows that the turning points corresponds to the intercepts, the x-intercepts of the quadratic function, the turning points, they correspond to the x-intercept of the quadratic function on the first derivative. And the point of inflection corresponds to the turning point of our derivative function. It corresponds to the what? To the turning point of the derivative function. So it was going to be something like this. All right, I'm just going to explain this one. Do not worry. So it is just going to be something like this. This is the graph of what? The first derivative, which is a quadratic. It was taken from a cubic function. So these two, they correspond the value of a from a cubic. If it is positive, on the first derivative, which is a quadratic, it is also positive. And the main aspect is here on the turning points. What is representing the value of x at your turning points of the f of x? Those values of x are the ones that you are considering as your x-intercepts on the first derivative. The value of x at the point of inflection is the value of x at the turning point of what? The first derivative here. So that is the condition. We've got our x-intercept on the what? On the first derivative from the turning points. So we can conclude that from this idea or information that we are having now, all right, we can just put it into consideration that the x-intercepts of what? The x-intercepts of the first derivative graph function here occurs when we have the turning point there on F. And what is the condition of the turning point? What is the condition of the turning point for any graph? The first derivative is equal to 0. So thus, when the first derivative with respect to x is equal to what? To 0. That is when we are talking about what? Stationary points of what? Of the original function. When the first derivative is equal to 0, that's at what? At the TPs, turning points of what? Of f. Those are the turning points. At the turning point, the value of x is the one that you're considering here. The first derivative. Another condition, the turning point of our first derivative occurs when occurs at the point of inflection. And we do understand that at the point of inflection, the second derivative is equal to what? Is equal to 0. Remember that concept. So therefore, we can conclude that the turning point, all right, in this case, our turning point on what? Of the turning point of what? The first derivative function, all right, occurs when the second derivative is equal to 0. When the second derivative with respect to x is equal to what? Is equal to 0. Thus, the condition of what? The point of inflection of what? The original function of f of x, the cubic function that you were given before. At the what? At the point of inflection of what? The original function f of x. This is the whole idea that you need in attempting questions with this idea. That you can answer any question, anyone, knowing this relationship between the original function and its derivative. So this is for a cubic function. Like I said, we have this one of a quadratic function, which is going to give us a linear. And we saw that when it is a linear, it is just going to give us a line that is what? A straight line parallel to the x-axis. So typical questions can be like this, all right? I just want to consider this as an example, but we're going to add more questions considering typical exam questions actually, so that you can understand much better. Here we are given the graphs of y is equal to f of x and y is equal to the first derivative of that f of x are shown alongside. So for proper understanding, when f of x is given is a quadratic, as we can see, we are dealing with what? A quadratic. Its derivative is what? Is a linear, exactly what we had from this presentation, that a quadratic will give us what? A linear. So if I was to properly represent, what is important here is what? The turning point of the quadratic, which corresponds to the x-intercept. The turning point of the quadratic which corresponds to the what? To the x-intercept. If I was going to have this here, it was just going to be something like this, all right? I just want to present this, our first derivative, all right? So let's say this is our x-axis like this. It was going to be an increasing function or an increasing graph, as it is here, increasing, passing through -4 and what? -4 and 1, something like this. But what I want us to see, what I want us to consider is the turning point of what? The turning point of A, this one. The turning point of F. It is your x-intercept here of what? The graph of the first derivative. It is your what? Your x-intercept. That is the condition. All right. I just took this graph here so that we can properly see what is happening. So at A here, it means the value of x at A is what? Is 1. At A, the value of x is going to be 1. What we do not know is the value of y. This is the condition, guys, of what? The first derivative. At the turning point, the first derivative is equal to what? Is equal to 0. All right, so our questions here were given from this. What is the gradient of the tangent to f at x is equal to 0? At x is equal to 0. If a tangent was drawn to f here, at x is equal to what? At x is equal to 0. What was going to be the gradient? All right. So here they are simply testing us, guys, here. They want to test our understanding if truly we do understand this relationship between the function and its derivative. Remember, the graph of the derivative, guys, it was taken from f of x. And our f of x being what? A quadratic. We know that when you are to refer to the gradient of a tangent, it is the first derivative with respect to x. Remember I said, guys, that the first derivative with respect to x is equal to what? The gradient of the tangent mt at that what? At the given point. At the given point. So in our case, if m is the first derivative at the given point where x is equal to 0, and we do not have that expression for the first derivative, but we have a graphical presentation of that first derivative. So just look into the first derivative where x is equal to what? Where x is equal to, suppose it's happening at a point where x is equal to 0 on the first derivative. So where x is equal to 0, I talk about what? In the y-axis, that's where x is equal to 0. So thus, the value of y is what? -4. When x is equal to 0, the graph of what? The first derivative passes through the y-axis at -4. When x is 0, y is what? -4. So the y-intercept there is the gradient of the tangent at x is equal to, it is at x is equal to 0. The y-intercept of what? The first derivative. That is it. So in our case, the gradient of the tangent when x is equal to 0 is what? -4. The y-intercept of what? The first derivative when x is equal to 0. This is what it means. You are in the y-axis when x is equal to 0, but on the first derivative function. Number 2, what is the x coordinate of point A? the x-coordinate of point A, remember, is a turning point. So its x-coordinate corresponds to the what? X-intercept of the first derivative, as we had before, and we say this is what? 1. At point A, x is equal to what? X is equal to 1, right? Number 3, what are the coordinates of what? Of B. B represents the x-intercept of what? Of f. What can we use? All right, this has nothing to do with the derivatives or what. Since we know the x-coordinate at A, and this one, the x-intercept here, because it passes through the origin, it means we can have the x value at B. The x value at the turning point, all right? So this is number 3. The x value at the turning point, remember, it can be given as x1, and this is x2. It can be given as x1 plus x2 over 2, where x1 and x2 are the x-intercepts. The x value at the turning point, which is at the turning point, our x value is what? 1. The value of x at point A, our turning point, is 1. It is equal to x1, the x-intercept, that's a 0 there, plus x2, which is the x value at what? The x value at point B, over what? Over 2. We can have the x value at B. So this is over 1. In order for us to solve this, that's 2 times 1, which is 2. All right, 1 times this, that's going to be B. X at B, 0 plus x at B. So the value of x at B is what? Is 2. Remember, we are referring to the x-intercept. So the value here is what? Is going to be 2. So that's 2, 0 as a point. Remember, this is y is equal to 0 in the x-axis. So therefore, the point B is going to be given as what? As 2, 0. This is our point what? Our point B. From our understanding of that graph, we can actually apply it that way. All right? So that is how we play around with these questions. You have the value of what? Of B there. So that is it. That is it from the x-intercept of the original graph as it was. Then determine the equation of f. All right? So to find the equation of f, our original function, all right, we are limited because we just have these x-intercepts. We do not have the what? The y-intercept. We just have the y value there to say, I mean, the x value, that is 1. We do not have the value of y. But we do understand, let us take our f of x, because we know that it is a what? A quadratic function. We do understand that our f of x was going to be taken as ax squared plus bx plus c. All right, ax squared plus bx plus what? C. But from f of x, we are limited so much because of the information that we have. We are limited. So what about from the second derivative? All right, in our case here, c is equal to what? Before that, let us see. Remember, c is the y-intercept, and the y-intercept is the one at the origin. Y is equal to what? Y is equal to 0 there. So it means f of x is equal to ax squared plus bx. All right, as we can see, c is equal to 0, so there's nothing there. But still, we are limited because of the information that we have, which is just the value of what? The x-intercepts. What about if we use the first derivative to find the value of a and b? All right, the first derivative is going to give us what? Let's see. 2 times a, that's going to be 2ax plus what? Plus b. This is our first derivative, which we have all the properties, the y-intercept and the x-intercept. Those are the most important properties. So now let us figure out what is happening from our first derivative and the properties. All right. Number one, to find the value of the first derivative from what we have here, or from the first derivative that we are given here, there are some things that we know automatically from our graph. This is the graph of the what? First derivative, which is a linear, remember, y is equal to what? Mx plus what? C. Where C, this one is the y-intercept, M is the what? The gradient. So C is the y-intercept. We have that the y-intercept there is what? -4. What represents the y-intercept on our first derivative here? It's what? It's B. That's our y-intercept. That is our B. So meaning to say automatically from this understanding of the graph to say the first derivative is a linear function and its y-intercept is going to be the value of B. Well, that is your y-intercept. So therefore, automatically here, B is equal to what? -4. That's the y-intercept. Y-intercept. Y-intercept of what? The first derivative. Since we are dealing with what? The first derivative. So what we need is the value of A. How can we find the value of A? We can use a point. Because, guys, when you say the first, it's like this. Okay, let me write it this way so that you can understand. It's like y is equal to 2ax plus b. Our b, we have it is what? -4. Y is equal to 2. That is what it means here. From the first derivative. So it means if we understand it in this manner, that is the same as the equation of a line like this, you can find the value of A by substituting the point where we have X and what? X and Y. Any point besides what? 0 - 4, the one that we had here. We can use any other point. There is a point 1, 0, the x-intercept. So you can find what? You can find A from there. From what? From the point 1, 0, the x-intercept. Y is what? It's 0. Where x is what? Where x is 1. So let us solve for A. -4 to the other side, that's a +4, which is equal to 2A times 1. That is what? That is 2A. If you multiply that part, we're going to obtain 2A. To find A, simply divide by what? Divide by 2 both sides of your equation. So 4 divided by 2, that is what? A 2. So we have the value of A from this. So therefore, our function f of x can be given or can be written as, remember, we said from that f of x, c is equal to 0. So this is what we remained with, where we just needed the value of a and the value of what? B. So a is what? 2. So therefore, f of x is going to be equal to 2x squared. Our b is what? -4. So that's going to be -4x like this. So this is the whole idea of your what? Your functions, all right? The whole idea of our function in this case. Our f of x, the quadratic, the original function that we had, not given anything from there, but we can use the understanding of its derivative because they are all, everything is there, like x-intercept and the y-intercept, we can use that. Then another part is sketch the graph of what? Y is equal to the second derivative of what? X. The first derivative is a linear function, and this is what we have here on your first derivative. All right, our first derivative is a linear function where we have it. Remember, a is what? Is 2. So you can substitute that 2 here. 2 times 2, that is going to be what? That is going to be 4x. Our b is what? Our b is negative 4 like this. This is our linear function, this one, our first derivative. So the question is, we are supposed to draw or to have the graph of what? The second derivative now. So simply differentiate that because you have the first derivative already. So what is going to be your second derivative? So if you differentiate, remember this is a linear. So you're going to have a constant. If you differentiate 4x, it is going to give us what? A 4. All right, the derivative of a negative 4, that's a 0. A constant gives us what? A 0. So this is what? Our second derivative is a what? A straight line again, y is equal to 4, which is parallel to the what? To the x-axis. Remember, I talked about this here. Say if you are given, because the first derivative gave us what? The first derivative gave us a linear. When we differentiated a linear function, we are going to obtain what? A line parallel to the x-axis. Exactly the idea there, y is equal to a. This is what we are obtaining here. Y is equal to 4. So you're simply going to draw a line parallel to the x-axis passing through the point 4, something like this. All right, so let's say this is 4. The line is going to be y is equal to 4. That is what? The second derivative. Graph of what? The second derivative. Just like that. So you see, guys, it's all about revision. So this was just for revision purpose. I want you to do more questions of this nature, where the second derivative, the first derivative is related from the original function. What are the properties that you must put into consideration? So do revision on that part. So that is it. Till we meet again.